I am Dr. Juluru Sandeep, Assistant Professor in the Department of Aeronautical Engineering, Institute of Aeronautical Engineering College. In today's lecture, I am going to discuss about a numerical problem on one-dimensional convection diffusion in computational aerodynamics and turbulence modeling subject. So we have covered the finite volume methods. So in the finite volume methods, I am going to discuss about this particular problem, one-dimensional convection diffusion problem. So as we all know, what is the importance of convection and diffusion in the transportation phenomena? So convection leads to the molecular bulk amount of transportation, whereas diffusion represents the molecular level transportation. So here we are considering a property pi is transported by means of convection and diffusion through one-dimensional domain as shown in figure. The boundary conditions of this domain are given as pi naught, that is at x equal to 0, pi equal to 1, and at x equal to L, pi is 0. So using 5 equally spaced cells and the central differencing scheme, calculate the distribution of pi as a function of x for u equal to 0.1 meters per second and compare the results with the analytical solution. So here the analytical solution is given by the equation pi minus pi naught upon pi L minus pi naught equal to exponential rho u x upon gamma minus 1 exponential rho u L upon gamma minus 1. So let us see how this particular problem is going to be solved by using the finite volume methods. So as we know, the finite volume method initially integrates the governing equation in the discretized cells, and then by giving the approximation for the flux variation, the discretized equation is obtained. That discretized equation is solved for the given boundary conditions to find out the unknowns in the problem. As the domain is divided into 5 equal parts, so since length is equal to 1 meter, so delta x 5 equal parts will give delta x equal to 0.2 meter. Here the boundaries are denoted by capital A and capital B. So in the previous slide also we have seen at these boundaries pi equal to 1 and at x equal to 0 pi is equal to 0. Okay, so we know the finite volume method notations. The center point is taken as P, the solution point, and towards right it is taken as capital E, and towards left it is taken as capital W. And the cell faces are denoted with small letters, small w and small e. So it is a uniform gridding spacing, so such that the distance between the points is delta x. The governing equation of steady convection and diffusion of a property pi in one-dimensional domain is given by d by dx of rho u pi is equal to d by dx of gamma into d pi by dx. So this equation is integrated for all the cells and then discretized with the approximate across the faces. So since this is a steady flow problem, so the continuity equation can also be considered, d by dx of rho u equal to 0. So this is the representation of the finite volume cells. The capital P center point and small w is the cell face towards left and small w is the cell face towards right, and capital E, capital W are the neighboring nodes. So integrating the transport equation over the control volume as shown in the figure. So if you are integrating it about point P, the node P, so that integration will varies from the lower limit east cell to the upper limit west cell. So such that here we are obtaining rho u a pi of E minus rho u a pi of W. So here capital A represents the area across the nodes. It is constant. So such that always it is given capital A. And similarly towards the right we have gamma d pi by dx. So it is also integrated between east and west cells such that it is given gamma a d pi by dx of E minus gamma a d pi by dx of W. So similarly integrating the continuity equation will gives rho u of capital A of E minus rho u a of W equal to 0. So this small w small e represents the cell faces. So the next step is to get the discretized equation at which we have to approximate the fluxes. So before going that we are defining here two variables capital F and capital D, where capital F is the convective mass flux, that is capital F equal to density into velocity rho u. And similarly the diffusion conductance capital D equal to gamma by delta x, the concentration gamma upon delta x, it is given here. The cell faces of the variables F and D can be written for each phase separately. So since we have the point P, E, W and small w and small e. So across the phase W, it is taken Fw equal to rho uw, and across phase E, it is taken Fe equal to rho u of E. So similarly, dw and de is also taken across the phases small w and small e. So since it is a one-dimensional domain, the area can be constant considering AW AE equal to capital A. And applying the central differencing scheme, the equations can be reframed based upon the differencing approach we are using. So here rho u, or in all the cases capital A can be cancelled, then rho u of E, that is Fe and pi E, minus rho u of W is Fw pi W. Then gamma d pi by dx. So d pi by dx is taken based on central difference, that is pi E minus pi P d pi. Okay, and gamma by dx is nothing but dE. So similarly for this term, d pi by dx, that is dp minus pi W. Then gamma by dx is dW. So such that we got the discretized equation, that is equation number 9. So we can further simplify this equation with some constants. So since the central differencing approximation is used to represent the diffusion terms which appear on the right hand side of equation 9, and for the left hand side terms, convective terms, the linear interpolation is applied. So because of uniform grid cell, so pi E is taken the average of pi P plus pi capital E. So similarly pi small w equal to pi capital W plus pi p by 2. So substituting these terms in equation number 9 will give Fe by 2 pi p plus pi e minus Fw by 2 pi W plus pi p equal to dE of pi e minus pi p minus dW of pi p minus pi W. That is equation number 11. So rearranging the above equation such that pi p is the unknown taken to left side and known values pi w and pi e are taken to the right side. To make this equation more simplified, so we are taking the left hand side also in terms of right hand side terms dw plus fw by 2 and dE minus Fe by 2, and the remaining term is going to be Fe minus W. So such that we can correlate these two terms as AW, that is dW plus Fw by 2, and AE, dE minus Fe by 2. So such that AP equal to AW plus AE plus Fe minus Fw. So this is how the final form of discretized equation is obtained. Equation number 13. So now we will try to apply it for the given problem. The discretized equation has the 5 nodes, in which node 1 and 5 are boundary points which has to be treated separately. So for equation 1, there is no left element, so such that the pi a is considered as pi w equal to 1. So here the node 1 is considered as P, so such that it does not have this is the actual discretized equation. So this we are applying it for point 1. So such that Fe plus pi b plus pi e, it has the right east cell, so pi e is as it is, but it does not have the left cell, so it is taken as Fa pi a. And pi e minus pi p minus, in place of dw it is taken as dA pi p minus pi a. So similarly for volume 5, that is other end of the domain B, that is pi e equal to pi b equal to 0 as given in the problem. So similarly the same equation is applied here, and the east is taken as B and west is as it is. So we got the equations 195 for nodes 1 and 5. So similarly by substituting it for the internal points 2, 3, 4, 5, we get by using the values dA, dB and Fa, Fb, the discretized equations are obtained with the central nodes. Okay, equation number 17. Equation 16 is for the boundary nodes. So that is node 1 is taken as AW equal to 0, there is no west element, or the value becomes 0, and AE equal to D minus F by 2, SP equal to minus 2D plus F, and SW equal to 2D plus F into pi A. So these values you can obtain it from this formula: AW equal to DW plus FW by 2, AE equal to DE minus FE by 2, and AP equal to. So for each node 1, 2, 3, 4 or 5. So you have to consider the west element. For one node the west element is A and east element is 2. So for second node the west element is 1 and the east element is 3. So like that for each node you have to identify the left and east elements and based upon that you have to calculate the AW, AE values. So once you have obtained that values, then comparing equation 16 with 13, you have to identify the SU and SP values. So by that we get the coefficients for all the discretized equations at respective nodes. So that system of equations will be written in a matrix form. So here we have taken the values. So initially the equation is like AP pi P equal to AW pi W plus AE pi E. So here for the first node we are going to consider AP and 1.55. Okay, there is no AW. So AE equal to minus 0.45. So it becomes like AE pi E minus AW pi W equal to 0. Okay, so here the constant is 1.1. So it becomes to the right. So second node, the AW. So AW is 0.55. So when it comes to the left side, it becomes minus AW. So minus 0.55. And AP is 1 and AE is 0.45. But in the equation it is negative. So minus 0.45. And pi 2, these are all zeros. So considered as zeros. So then node 3, AP, AW minus 0.55, AP is 1 and AE is minus 0.45 and constant is 0. Similarly, fourth node minus 0.55, AW, AP is 1, AE is minus 0.45 and constants is equal to 0. And similarly, the last node AW is minus 0.55 and AP is 1.55 and constant is equal to 0. So this matrix form, if you observe, it is in a tridiagonal matrix, that is, it is having only the lower diagonal elements, minus 0.55 and the middle diagonal elements 1.5, 1, 1, 1, 1.45 and the upper diagonal elements. So such that this matrix is named as tridiagonal matrix, is solved by using the Thomas algorithm, which we have used in the previous problems also. So this tridiagonal matrix method is a two-step process. So in the forward step, all the lower diagonal elements are made to 0 and the diagonal elements are made to 1, and in the backward step we are going to go from the bottom to top, so such that solving them will give all the unknowns, pi values. So we are going to do the row manipulations by using this formula. So here we consider the equation A, B, C, the coefficients. So for first equation we have only BC and this we consider it as D, the constants here. So second equation has A, B, C. So the modified version is denoted with dash. So C1 dash equal to C1 upon B1 minus A1 C naught dash. So by substituting the values, we are going to get the next values, and at the end we are going to get this unknown values pi 1, pi 2, pi 3, pi 4, pi 5. So this is the resultant solution of this finite volume method for the one-dimensional convection diffusion problem. So if you want to compare this result with the analytical solution, we have to use the equation number 1. The equation number 1 is pi minus pi naught upon pi L minus pi naught, which is equal to exponential of rho u x upon gamma minus 1. So here the length is 1 meter, density is 1 kg per meter cube, gamma equal to 0.1 kg per meter second. So if you are going to substitute this, we know pi naught is 1, pi L is 0, minus 1, which is equal to exponential of rho u x. So 1 into 1 into x upon 0.1. Sorry, u is 0.1 minus 1 upon exponential of 1, 0.1, 0.1 minus 1. So what we will get here, pi minus 1 upon minus 1 equal to e power x minus 1 upon e minus 1. So we know e value is 2.7183. So we can write pi equal to e power x minus 1, 1.78. So this is into minus 1. So plus 1 you will get here. So this is into. So what you will get here, 1.78. So 2.78 minus e power x upon 1.78. So that is what here written in equation 15. Pi of x equal to 2.7183 minus exponential of x upon 1.7183. 7183. So substituting x distance 0.1, 0.3, 0.5, 0.7, 0.9. So we are going to get the analytical solution. We have to take exponential of 0.1, exponential of 0.3, 0.5, 0.7 like that. So these are the finite volume solution. The difference is given and the percentage of error is given. So as the distance is increasing from the 0.1, the error is also changing. So this is how the finite volume methods are used, and we have to compare the results with the analytical solutions. So this we can do it for the further cases, u equal to 2.5, u equal to different cases. So you can see the graph between the analytical and numerical solution, it is almost same. So you can go for 0.2 or 0.5 or for different cases, and you can check the finite volume method efficiency. So this problem is taken from the Versteeg finite volume methods. So in the given problem, it is given case 0.1 meters per second. So this u value you can change and you can get the solution for further problems. Thank you. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.